Hello everyone and welcome back. My name is Mr. Koval, and today in this video I'm going to be going over the different relationships that involve the enthalpy of a reaction. And so in previous videos we talked about how there's a relationship between the enthalpy of a reaction and the equation itself. So we can tie the different coefficients of each product or reactant with the delta H of the reaction given, so that way we can use it as a conversion factor to convert from a certain amount of energy evolved for a reaction to a certain amount of product that was made, or to a certain amount of reactant that was needed to have the reactant go. So there are other relationships that we can talk about with regard to delta H of a reaction. And so there's three main relationships that I want to go over and give examples for, because this is going to be useful for future problems when we're trying to figure out the delta H's of different reactions or reactants. So the first relationship is that if you have a chemical equation and you multiply that chemical equation by a factor, then you can multiply the delta H of the reaction by the same factor. You must multiply that together. And that makes sense because we saw that there's a relationship between the balanced equation, the coefficients in the balanced equation, and the delta H of the reaction. So that if you're going to double the reaction, then of course you're going to double the delta H that goes with the reaction, because there's that one-to-one relationship based on the balanced equation and the stoichiometry. So that's the first thing. So you can see this in this example here, that if I have an equation, it's A plus 2B, and that gives me the product C, that has a delta H of the reaction, delta H1. If I multiply this equation by 2, I get 2A plus 4B gives me 2C. So if I multiply the equation, then I must multiply whatever the delta H of the reaction is by that same factor, which is going to be 2. Because there's a 1, like for example for A, there's a 1 mole of A gives me whatever delta H is. 2 moles of B gives me whatever delta H1 is. So if I double these, then I also double the amount of double H, or the delta H that I am getting. So that's the first relationship. The second relationship is if a chemical equation is reversed, then you have to change the sign of the delta H of the reaction. And the main reason for this is because delta H of a reaction is a state function. It doesn't depend on how you got there. It just depends on the initial and final states. So if you're going to reverse the reaction, then what you're doing is you're flipping those states. The final state becomes the initial state, and the initial state becomes the final state. And so what used to be final minus initial then becomes initial minus final. So you're flipping those. And so if you're flipping those, then you're going to change the sign. So the magnitude doesn't change, but the sign does. So here we have A plus 2B gives me C again. Now we're going to reverse it. C gives me A plus 2B. And the difference is that I take the negative of the delta H of that reaction. So delta H1 becomes negative delta H1 for the reverse of that reaction. And the final relationship is that if I have a chemical equation that can be expressed as a sum of different steps in the equation, right? So if I have steps or chemical reactions or chemical equations that are multiple steps, and those can add up to the final equation, then so do the delta H's or the enthalpies or the heats of those reactions will add up to the delta H or the enthalpy of the reaction of the overall reaction. So to express that, here we have two steps in a series, and they add up to this equation here. So I have A plus 2B gives me C again. And so here, this is a delta H1. And then I have C goes to 2D. That's going to be a delta H of 2, a delta H2. if you add these together, the c's on both sides cancel out, and so I get an overall equation of a plus 2b gives me 2d. So these two steps, or steps in the equation, will add up to this one. They both have their own delta H's of reaction, or heats of reaction. So the heat of this reaction is just going to be these two added together. So delta H1 plus delta H2 gives me delta H3, which is the heat of this overall reaction as well. This is also known as Hess's law. Hess's law will be very important later on. But if you understand that these three relationships, then you can manipulate equations and add them together to get overall equations to figure out like what your target equation, what the heat of that particular reaction is. Okay, so I hope this is clear. In the next video, I will go over example problems or practice problems where we will be using these relationships to solve the problem. I hope this was helpful. If you have any questions, please put them in the comment section. Let me know what you think. Let me know if there's anything you want me to go over. Also, if you like this video and you found it helpful, please share it with your friends. Hit the notification bell if you want to be notified for any other videos I put out. Make sure you subscribe, hit the subscribe button, and thanks for joining me, and I'll see you next time.